350 years ago comes in. In 1654, a German inventor showed off his new air pump with a demonstration of the incredible power of, well, nothing. Physicist Toby Ferenczi sets out to recreate the experiment for me.
This is one of the most famous experiments in the world, isn't it?
Absolutely.
I'm not being rude. I just expected to see something a bit more obviously scientific.
It's very simple. It's just two hemispheres made of solid steel.
It looks like cookware.
Yeah, basically.
There's no mechanical bits inside, no flashing lights.
No. It'd be great for ratatouille.
Inventor Otto von Guericke wanted to test the role of air in breathing and burning. So he set out to create a vacuum and invented the air pump. To show the Emperor of Germany how well his new pump worked, he started by sucking the air out of a sphere.
And this is it, just 3 parts?
Yeah,
so every part is crucial.
Right. And then I have to try and get the top piece on top of it. There we go. And then, crucial part of the experiment, the vacuum pump. All it does is suck air.
So that's what makes our vacuum in there?
Exactly.
OK.
Turn it on, and now we're sucking.
So this is what's fixing these 2 hemispheres together, pulling the air out.
Now in there's less air in there than there is out here.
To replicate von Guericke's experiment, we need one other ingredient: horses.
3, 2, 1, pull!
But we haven't got any. We do have football players.
And they're here to help me prove that nothing is stronger than a football team. But only if nothing is in the right place. Come on, guys, give it some heave. Oh!
Von Guericke set 2 teams of horses to try to pull the hemispheres apart. And that's what these football players are going to attempt.
Right, I think this should be about ready.
OK, so that's cooked.
Yeah.
There really is nothing in there. We need some blokes, don't we? Right. Can I have the strong men, please? Over here. Time to be strong. Come on, chaps. OK, let's have 2 on that side, 2 on that side, first of all. I think we'll ramp this up slowly. So if you take the strain. OK, when we're ready, pull. Give it everything you've got, boys. There's nothing in there. This is held together just by the vacuum that we created. Come on. Look at their faces on it. Come on, boys. 1, 2 more. Let's get them on. All right, come on. Go on, give it some heave. There's nothing in there. Right, let's have the last 2 on. We've got everybody on now. 1, 2, 3. Oh, now they're getting serious. Oh, come on, you know what's in that sphere? Nothing. I mean, look at the size of this bloke here. That's a big lad, a big, strong man, and you're being beaten by nothing.
It's true, there is nothing inside the sphere. But because air is a gas, it flows all around the outside of the sphere, creating almost 15 pounds per square inch of pressure against the 2 halves and pushing them tightly together. That's like holding 150 pounds of weight in the palm of your hand.
The only thing that's holding those together is the pressure difference. You have no air inside the sphere, and you have lots of air outside, so the pressure difference is huge.
So this is all dependent on pressure difference. It doesn't actually matter what the absolutes are at either end, but there's more pressure outside than there is inside.
Exactly.
Come on, lads, give it some.
Come on!
Come on!
Von Guericke's 16 horses couldn't manage either.
OK, guys, right, you can slacken off now. Your time is up. You have been beaten. Let's just get on the end of this thing and have a look, because I just want to do something here, if you're ready. It was easy. One tiny bloke did it when you lot failed, and that is the power of a vacuum. And that's how you keep the trolley gas platform pinned to the sea floor, by using nothing at all.
My research shows me the trolley designers used a 21st century version of von Guericke's hemispheres to secure the rig to the ocean floor. They did it by fixing a series of suction piles to the bottom of the troll's legs.
Here is my model of the suction piles. Obviously, the real thing's quite a lot bigger than this, about 40 times the length. But this is how they work. Essentially, they're just like an elongated cup, open at this end, and then at the top, the sealed end, an essential piece of kit, there is a tap. And that's what makes it all possible. And here's how it works. Here's my recreation of the seabed. It's a sort of gloopy, gluey mess. In texture, pretty much what it's like. So, if we put it in with the tap closed, so this is just like a cup, the big pile gets lowered, and very, very quickly, it becomes very hard to push down at all because, well, what's happening, obviously, it's sealed, and it's compressing the air in the top of the pile, and there's a lot of air in there to compress, and it'll only go so far, and then when it's gone in, well, it's all wobbly. It's sitting on a bed of compressed air. However, if we open the tap on the top, suddenly, the air can escape. It's not sealed. It just pushes neatly down into the seabed. If we close that tap, it's sealed again. So it's rock solid and steady. And in fact, it won't come out because what you're doing, you've created a pressure differential, and what I'm actually doing now is lifting the seabed out. Well, you can see some of the seabed coming out. There. I can't move it at all. It's become part of the seabed. Open the tap. It can come straight out. That's exactly how it works, only bigger.
Troll's 19 suction piles stand 40 yards high and are fully driven into the seabed. Not even 100-foot waves and hurricane-force winds can shift it.
All that remains now is to get to the bottom of what Trolley was designed for. And the answer to that is right there.
These are the pipes bringing the gas to the surface. So how do you get the gas out of the ground and back to Norway? That's where a racing car can help. When the Trolley gas platform first drilled down beneath the North Sea 10 years ago, it tapped into a gas reserve which poured out under its own pressure. The gas surged up to the surface and through 43 miles of pipe back to the mainland. But after 10 years, gas pressure has fallen.
This bottle represents the gas field, and inside, the fizzy drink is the gas. Now, obviously, when they drill into this for real, it's under enormous pressure. And there is a way of getting pressure in here straight away by using this. Inside the cap, these ordinary sweets glued to the inside of the lid, when I drill through, will drop into this, and they'll cause it to release all of the carbon dioxide from inside in one hit, putting it under immense pressure. Obviously, I'm not suggesting there are enormous sweets suspended underneath the surface of the sea. That's just to illustrate pressure. So we fix the cap on. Probably best if you don't try this at home, though clearly that's how we discovered it worked. I shall now commence drilling into my gas field. I've got a good idea what's going to happen. So have you, probably, but this will illustrate it. Drilling. We hit the gas field, and out it comes. So for a while, everything's very easy. It does the work itself. The gas just comes flooding out. But after a while, inevitably, the pressure is all equalized. That's at the same pressure in there as out here. It's not going to come out anymore, and it becomes a bit trickier. The only solution to that is you have to suck it out, which is a fairly tasty alternative in this instance, but for real, it's complicated, time-consuming, and expensive.
Engineers needed a solution, and it came in the shape of an antique car. Rewind to 1902 for the Paris to Vienna car race. On rough country roads, the cars hit speeds of almost 80 miles per hour. One driver, Marcel Renault, modifies his car and carries himself to victory. His secret, blasting more air into the engine. He invents the turbocharger.
This This is a much faster car than Marcel Renault's, but it's got a turbocharger that uses exactly the same principles he pioneered in 1902. This turbo makes the most gorgeous noise.